Hi, this is George Graybill, and I'd like to read to you another chapter from the book Stuff, subtitled The Foibles, Fiascos, and no, that's not right. The Fortunes, Foibles, and Fiascos of those who sought to understand matter. This is chapter 14, entitled Stranger and Stranger, or What the Stuff That Stuff is made of is made of. First, it was proven that stuff is made of atoms. Not too long ago, it was thought that atoms were the smallest things in the world, and that they could not be cut into smaller pieces. Next, it was learned that atoms could be split up, and that they were made of smaller bits called protons, neutrons, and electrons. Did you think that was all there was to know about what stuff is made of? Oh dear. It turns out that protons and neutrons are made of even smaller things called quarks. No, really, that's what they call them. Quarks come in 6 flavors: up, down, top, bottom, charm, and strange. A proton is made of 2 ups and a down. A neutron is made of 2 downs and an up. There are also 2 quark particles called mesons that appear during very high energy processes and decay into other things almost immediately. Here is a picture of one version of where it all came from. Quarks and stuff made of quarks have mass. Particles called leptons are not made of quarks, but they also have mass. There are 6 kinds of leptons, including their old friend the electron. 3 of the leptons are called neutrinos. It sounds like the name of a breakfast cereal, but it means little neutron in Italian. The term was coined by the famous Italian physicist Enrico Fermi. Quarks and leptons are classified as fermions, in his honor, I guess. Quarks and leptons account for everything in the universe that has mass. Hopefully you remember that stuff is matter and matter has mass. So stuff is all quarks and leptons. These 12 particles are part of what is called the Standard Model. But there's still more. In addition to particles with mass, there are also particles without mass that transmit forces between the ones with mass, that is, between fermions. These massless particles are called bosons. Hey, relax. There won't be a quiz on this. The particles exert force on each. When particles exert force on each other, they do it by exchanging bosons. There are 4 fundamental forces in the universe: strong, weak, electromagnetic, and gravitational, in order from strongest to weakest. First, the strong force acts between quarks and is caused by bosons called gluons. The scary part is that the force increases as the affected particles get farther apart. The electromagnetic forces are caused by photons. Remember photons? The weak force is observed in certain nuclear reactions. It is caused by several kinds of bosons. The force of gravity is by far the weakest force. It is thought to be caused by gravitons, but no one has ever been able to prove this or figure out why the force is so weak. Okay, this is really just a quick look at the Standard Model. Even this much was probably pretty tedious. The model has been very successful in explaining a lot about the nature of everything from the workings of atoms to the Big Bang that started the whole universe. With the exception of gravity, it explains all the forces and accounts for all the particles except one. the Higgs boson. It was thought for a long time that all that was needed was just one more particle to really wrap things up. Everything in the standard model suggested that something was missing. One of the people who really wanted to find this particle was Peter Higgs. The particle was named after him even before it was discovered. Eventually, enough physicists convinced enough people of the importance of this particle that more than 100 nations chipped in $9 billion to build the largest machine in the world in an effort to find the Higgs boson. And they found it. The machine is called the Large Hadron Collider. And here's a picture of Peter Higgs in front of the LHC, or Large Hadron Collider, detector that detected the boson. A hadron is a particle made out of quarks. And the purpose of the Large Hadron Collider, or LHC, is to see what happens when these particles collide at high speed. This is done by accelerating two beams of particles in opposite directions, aiming them at each other, and then studying the resulting mess. The two particle beams are usually both streams of protons. The protons travel in circles through tubes deep underground. Pretty much everything about the LHC is amazing. More than 10,000 scientists worked on building the LHC, which took 10 years to complete. The circular beam paths have a circumference of 27 kilometers. That's 17 miles. It would take about 7 hours to walk all the way around the tunnel that holds the beam tubes. Particles are accelerated at very close to the speed of light, which allows them to make 11,000 trips around the circle in 1 second. Data is analyzed in 140 computing centers in 35 countries. And here is part of the 25 kilometer tunnel at the LHC. Data is collected by particle detectors located at the 4 places along the circle where the beams cross. The detectors gather enormous amounts of data about the particles produced in a very short amount of time following a collision. The data includes the masses, momentum, energy, lifetime, charge, and spin of all the particles produced. And this is what the LHC detector picks up. Lines are particle paths, and blue splotches are energy. The Higgs boson has also been called the God particle. At some point, a physicist who for some reason found the particle annoying called it the goddamn particle. Eventually the name was shortened to God particle. Many people mistook the name to have something to do with God, such as, when we found the God particle, we would have completed the standard model and would then know everything, like God. Peter Higgs himself didn't like the term. He thought it was too sensational sounding, and also that it would offend people of some religions. The Higgs boson turned out to have properties almost exactly as predicted. It wrapped up the standard model very neatly. This actually disappointed many scientists. You don't get Nobel Prizes for discovering the expected. Too boring. You get them for explaining the unexpected. Of course, Higgs got the prize for his prediction based on the old find a particle, win a prize rule. Perhaps the most interesting thing about the Higgs boson is that it is what it does. It gives other particles mass. Does that sound odd? Isn't mass something you're just born with? You can tell you have mass, can't you? Do you remember a boson showing up at your door one day and asking if you would like some mass? Anyway, we should probably just be grateful. People have been paying a lot of attention to the LHC. As the day approached when the collider would be operated at full power, some people started to get nervous. Rumors circulated that the collisions would produce tiny black holes that might swallow the universe. Some people worry about everything. The scientists in charge took the worriers seriously enough to prove that there was nothing to worry about. They were obviously correct because we're still here. It should be explained that the nations of the world did not spend $9 billion just to find one crummy little particle. There is a lot to be learned from the results of collisions that occur at outrageously high energy. Here are some of the other results from the LHC. 1. The discovery of 4 quark particles that disappear almost immediately, but probably were present just after the Big Bang that kicked off the universe. 2. The collisions of protons with lead nuclei produced traces of quark soup, or QGP. This is a new state of matter that is denser than anything except the stuff inside a black hole. It is believed that for a few milliseconds after the Big Bang, it was all quark soup. Today's special: quark soup and a salad. $9,002,000,002. 3. Even though many physicists hoped the result of the LHC would suggest some wild new departure from accepted theories, almost everything so far has confirmed the validity of the Standard Model. Don't get the idea that because the Standard Model seems to be complete, physics is finished. There is still a lot we don't know about the nature of stuff, and there is hope that the LHC will give us a hand with that. Here are just a few of the unanswered questions, and they all sound a bit scary. The problem of Schrodinger's cat. Why can some things be in 2 states at once, but don't decide which to be in until we look at them? Dimensions. Are there more than 4 dimensions? Height, width, length, and time. The universe. Are there alternate universes? Dark matter. The motions of objects in the universe indicate that there is a lot of matter we can't see. Is it made of particles? Dark energy. Some unknown form of energy is speeding up the expansion of the universe. What is it? Time. Why does time have a direction? Does cause and effect always work? That is, can something happen without a cause? Why are all the physical constants, speed of light, force of gravity, etc., just right to allow life to exist? Are there other universes with different constants? How will the universe end, and will there be a sequel? Gravity. Can this force and the other 3 be explained by one theory? Also, why is gravity so weak? The other 3 forces, weak, strong, and electromagnetic, are explained by quantum mechanics and the Standard Model. Gravity is explained by general relativity. So can relativity and quantum be combined? What we need are gravitons, gravity particles. Where are they? Another way to put the question: are space and time continuous, or do they come in separate little bits, that is, quanta? A theory that combines relativity and quantum mechanics is referred to as a theory of everything. A lot of people have tried to find one, but even Albert Einstein couldn't figure it out. One popular approach is called string theory. We will try to explain the basics of this theory, but it won't make much sense. This is an artist's conception, or an artist trying to show the extra dimensions that are needed for string theory. Particles are usually thought of as points with no dimensions. String theory represents particles and forms of energy as one-dimensional strings. These strings vibrate in different ways, and how they vibrate determines whether they are matter, light, or gravity. The math on which the string theory is based is described as elegant. People like that. The feature that looks more iffy is that 11 different dimensions must be introduced to make the whole thing work. Also, there has been no experimental evidence to back up the theory, and yet many physicists think that string theory is the best hope for a theory of everything. We'll just have to wait and see. And that is the end of chapter 14. The next chapter, which is the last chapter, is titled Back Where We Started. What is subtitled, What is Stuff Really? Is matter your problem, or is matter your fault? If you scroll down, you'll see a link to a place where you can read the book, buy the book, read reviews and so forth. And if you look down in the lower right-hand corner of the YouTube screen, you should see a button called subscribe. And if you click it, you'll be able to subscribe to this YouTube channel. Okay, that's all for today. Last chapter coming up soon. See you later. Bye.